Hi everybody, we're going to look at two rather involved applications of calculus in this video. Two problems. The first one on what intervals is y equal to 1 over x squared plus 1 concave down. Now I've got it sketched over here to the right. We have a y-intercept of 1. I know that that y-intercept is 1 because if I substitute 0 for x, I get 1 over 1. Or 1. Okay. It also looks like we've got a point of inflection or a change in concavity both there and there. And it appears that we are concave down on this interval. And so we're going to use calculus to find x1 and x2. So on that interval, we're concave down. We just need to find out where that interval is. What are those x values? What are those input values? In order to determine where it's concave down, big picture, we need to determine where y double prime is negative. So where is y double prime negative is another way of saying where is y concave down. Well, to find y double prime, we first need to find y prime. I'm going to use the quotient rule. So y prime is low times d high minus high times d low over low squared. We can certainly clean that up because we know that x squared plus 1 times 0 is 0. And so we get negative 2x over the quantity x squared plus 1 quantity squared. There's y prime. Now if we were asking a question of where this function is increasing or decreasing, then we could say where is y prime greater than 0 or less than 0. But we're not asking a question of increasing or decreasing, we're asking a question of where it's concave down. So I need to continue by finding y double prime. So I'm going to derive y prime, and y double prime will again require the quotient rule. But before I do, let me rewrite this as negative 2x over x to the fourth plus 2x squared plus 1. And I'm doing that because I am expanding the square of this binomial, expanding x squared plus 1 quantity squared. We know that when we square a binomial, we square the first. So there's x to the fourth. Then we add, in this case, twice the product of the first and the second. There's that. And then we add the square of 1. I'm not going to use the chain rule yet because it's barely been introduced, and so we'll use the rules that we already have, which we have the quotient rule, and we certainly have a rule for deriving power functions. Okay, so y double prime. Well, y double prime is low, x to the fourth, plus 2x squared plus 1, d high, so times negative 2, minus high, so high is negative 2x, d low, 4x cubed, plus in this case 4x for our derivative of low. So again, I've got low, d high, minus high, d low, over low squared. Now I'm going to write low squared, stay with me now, as x squared plus 1 to the fourth. And the reason I'm writing it that way in this instance is because x squared plus 1 squared was low, which, yes, it could be written this way. I expressed it both ways. But to keep the denominator compact and to be efficient right now, if I square x squared plus 1 squared, I get x squared plus 1 to the fourth power. So we can clean this up. I'm going to distribute a negative 2 to that quantity. I'll distribute a negative 2x to that quantity, and I'll clean. And so I should get, let's see, negative 2x to the fourth minus 4x squared minus 2 minus negative 2x is the same as plus 2x, so that's going to be, let's see, plus 8x to the fourth, and then plus 8x squared all over x squared plus 1 raised to the fourth power. I'll clean one step further. combining like terms, negative 2x to the fourth, 8x to the fourth is 6x to the fourth. Okay. Let's see, what else? Negative 4x squared, positive 8x squared is positive 4x squared, minus 2 all over the quantity x squared plus 1 to the fourth. So there's y double prime. Quite a bit of work to get there. Again, this is a rather involved problem. And the question now that we need to go back to is, where is y double prime negative? So this is going to require some critical thinking. Where is y double prime negative? Well, your denominator, I want to focus on the denominator for just a moment, is x squared plus 1 quantity raised to the fourth. And what I want you to consider is, what's going to happen no matter what value you put in for x, what will happen? Well, if I put a positive number in for x, I get a positive squared plus 1 then raised to the fourth, which is going to result in a positive. If I put a negative value in for x, I get a negative squared, which is a positive, plus 1, which is still a positive, raised to the fourth, which is still a positive. And if I put 0 in for x, I get 0 squared, which is 0, plus 1, which is 1, raised to the fourth, which is still positive. In other words, my denominator, this piece, will always, no matter what, be positive. That's very important. If you don't get that, pause the video, rewind it 30 seconds, and reconsider. So the denominator will always be positive. Now, the question is, where will this whole thing be negative? Well, the only way that the whole thing is going to be negative if the denominator is already positive is if the numerator is negative. Okay? So let's consider that for just a moment. I need the numerator to be negative. And so I can write a simpler question. The original question is, where are we concave down, which is the same as saying, where is y double prime negative? And we've simplified the question by now saying, where is 6x to the fourth plus 4x squared, that's a 4, plus 4x squared minus 2 less than 0. Now, may not be obvious, but you want to factor this thing. So I'm going to pull out the greatest common factor, which in this case is a 2, times the quantity 3x to the fourth, let's see, plus 2x squared minus 1. So where's that less than 0? Okay, this is factorable. We spent some time factoring. You certainly spent some time factoring in pre-calc. I'm going to write 3x squared, x squared. So there's my, this product will give me my 3x to the fourth that I need. And now the question is, what do these two need to be in order to complete that? Well, if we play around with it a little bit, we're going to see that this should be a plus 1 and this should be a minus 1. And of course, we're still less than 0. You can FOIL to expand and check. In other words, that's a minus 1x squared, that's a plus 3x squared. That gives us the plus 2x squared that we're looking for. We've already got our minus 1, negative 1 times 1. We've already got our 3x to the fourth, 3x squared times x squared. Okay, so where is this whole thing? This whole thing negative. Now, I want you to again consider what we talked about up here. Consider something similar. X squared plus 1. No matter what you put in for x, no matter what we substitute for x, x squared plus 1 will always result in a positive. 2 is also positive. I need 2 times x squared plus 1 times 3x minus 1 to be negative. And so that tells me that 3x squared, I should say 3x squared minus 1, has to be less than 0. You've got a positive times something, and you need the result to be negative. Well, that's something, 3x squared minus 1 then, has to be negative. So we say 3x squared, take away 1 is less than 0. It's the only way that'll be, the only way that our second derivative will be less than 0. I'll add 1, 3x squared is less than 1. I'll divide by 3. X squared is less than a third. Okay. And now we need to think about this. What values squared would result in something less than a third? take a couple of minutes and consider, maybe a few seconds, maybe a couple of minutes, and consider. I'm going to draw, so you might want to pause the video, but I'm going to draw a number line now. Okay, there's 0. If I took the square root of both sides, it might help you consider the fact that x needs to be less than the square root of a third. Okay, less than the square root of a third. But if it's greater than the opposite of the square root of a third, I'm also okay. In other words, all values between negative square root of a third, if you consider the number line, negative square root of a third and positive square root of a third, will make this statement true. X squared is less than a third. Okay? And if this statement's true, then this statement's true. And if this statement's true, then this statement's true. And if this statement's true, then our numerator is negative. And if our numerator is negative, then our second derivative is negative. Okay? Now, one other way to think about it, or one other way to consider these values, is you could say 1 over the square root of 3 is less than x, which is less than the opposite of 1 over the square root of 3. Because the square root of 1 is 1 and the square root of 3 is the square root of 3, so that's another way that we could write this. Additionally, you may remember from your work with radicals in a prior course that we could also call this root 3 over 3 less than x less than negative root 3 over 3. They all work, different ways to write it. So I should say, to finish this problem, we now know the inputs that we were looking for from the start. x2 would be positive 1 over the square root of 3, and x1 would be negative 1 over the square root of 3. We could also say that this function y is equal to 1 over x squared plus 1 is concave up when x is greater than 1 over root 3, union when x is less than negative 1 over root 3. Our next problem is also going to take a bit of time. We want to know on what intervals y equals x to the fourth minus 4x cubed is both increasing and concave down. And much like in the last example, I'm going to use some number lines to answer this question. So what we want to know is, where is y prime, first of all, where is y prime positive? And at the same time, I'm going to say union, y double prime negative. So we're going to use calculus to determine that. Okay. So y prime is equal to 4x cubed minus 12x squared. I can factor out a 4x squared. And when I factor out a 4x squared, let's see, we're left with x minus 3. Now, the only times, if you think about it, the only times that y prime will equal 0 are when 4x squared equals 0 or when x minus 3 equals 0. So y prime will equal 0 at, or when x is equal to 0, and also when x is equal to 3. So I'm going to draw a number line. Stay with me here. I'm going to draw a number line. Okay. And this number line is meant to represent y prime. Now I know that at x equals 0 and at x equals 3, okay, so there's x equals 0 and there's x equals 3, I know that the derivative is equal to 0. Now if you go back for just a moment, those and consider that those are the only times the derivative is equal to 0, because either this 4x squared must equal 0 or this x minus 3 must equal 0. In other words, the derivative is 0. The first derivative is 0 at x equals 0, at x equals 3, and it's not 0 anywhere else, because there's no other values that I could put in that would make the derivative equal to 0. So everywhere else the function is either going to have a positive derivative, in which case it would be f of x or y would be increasing, or the function will have a negative derivative, in which case y would be decreasing. So I'm going to check around these values now. I'm going to check around them, okay, and use that information to determine where the function is increasing and where it's decreasing. So if I select a value over here, something that's less than 0, I'm going to pick something easy like -1, okay? Pick something, test, I'm going to test to the left of 0, so over here, I'll test. And I'm going to put -1 in, and when I do, I get 4 times -1 squared, that's 4, times -1 take away 3 is -4. I get a -16. In other words, y prime is negative, y prime is less than 0 when we are left of 0. Okay? So on this entire interval over here, the function is decreasing. It has to be, because it can't cross the x-axis again. Now let's test on this interval. Okay? So I'm going to pick a number between 0 and 3. I'll choose 1. I'll put 1 in. Okay. So let me erase this. And when I put 1 in this time, okay, I get 4 times 1 squared, that's 4, times 1 minus 3 is -2. I get -8, which means that the function is also negative. The derivative is also negative on that interval, which means that if y prime is negative, the function is also decreasing there. So the function was decreasing over here. Then it stopped decreasing instantaneously, and then it's decreasing on this interval as well. Now let's test at a value greater than 3. So I'm going to pick 4. Okay? If I put 4 in, I get 64 times 1, which is positive, and that's all that matters here. Okay? So my derivative is positive over here, which means that if y prime is greater than 0 over here, the function's increasing on that interval. Now, keep in mind, we've only answered questions about where the function is increasing and concave down. Okay? So it's increasing whenever x is greater than 3. So now to the question of where is it concave down. I'm going to draw another number line. Bear with me here. And we're going to label this number line y double prime. And I'm going to start by determining where y double prime is equal to 0, and then I'll test around those points to determine if y double prime is positive or negative, which would indicate whether it's concave up or concave down. So here I've got a function for y prime. Y double prime then is 12x squared minus 24x. Which we could write as, we could factor out a 12x, and we could write it as 12x times the quantity x minus 2. The zeros of y double prime, in other words, the places where y double prime is equal to 0, they occur again at 0. Notice I'm lining up the number lines, so that 0 lines up with the other one. So I've got a 0 for y double prime at 0, and another one at 2. In other words, y double prime is equal to 0 here, and it's equal to 0 here, and it's not equal to 0 anywhere else. There's nowhere else that y double prime will equal 0. We can see that from its factored form. So I'll test over here. I'll test in here in this interval. I'll test in this interval, and that'll tell me the sign of y double prime, positive or negative. So I'm going to do each of those. So I'll start here. So pick a number less than 0. Let's say -1. Put -1 in for x, and we get -12 times -3. -12 times -3 is 36, which is positive, and so y double prime is positive here. Okay, y double prime is positive there. So in other words, on this interval, when we are less than 0, okay, on that interval, y prime is positive and y double prime is negative, so the function is decreasing and concave up. Okay? Now, we want to know where it's increasing and concave down, so we haven't found a spot yet, where an interval yet where that's true. Let's test our next interval. So I'm going to pick a number between 0 and 2. The logical one to pick would be 1. So I'll put 1 in here, and I'll put 1 in here for x. I get 12 times -1, which is negative. Okay, all I care about is it positive or negative, because that tells me about concavity. So in this instance, y double prime is negative on that interval from 0 to 2. So here we're decreasing and concave down from 0 on that interval from 0 to 2. Okay? Now, when we are greater than 2, so over here, I'm going to pick a number greater than 2. I'm going to choose 3. So I'll put 3 in. I'll put 3 in. 12 times 3 is 36. 3 minus 2 is 1. 36 times 1 is 36. Most importantly, y double prime is positive, which tells me that we are concave up. Okay, we're concave up. Now the question again was, where are we increasing and concave down? In other words, where is y prime positive and at the same time y double prime is negative? So let's look at our number lines. We need to look at them both at the same time, and we're looking for intervals where that's true. Okay? Over here, y prime is negative, so we're decreasing, so that's out. Okay, that's not even an option. On this interval, we're still decreasing. Okay, so that's out. That's not even an option. It's on this interval that we are increasing. Okay, and in fact that's the only interval where we're increasing. And so the question is, where are we increasing and concave down? And if you look, there is never, okay, so look from here over, there's never an instance where we're actually increasing and concave down. So nowhere is our answer. Okay, but that might leave you a little sad because it's kind of, we did a lot of work to get an answer of nowhere. That's got to be okay, but let's ask a different question just for kicks. So let's change it to decreasing concave down. Where are we decreasing concave down? In other words, f prime is negative and f double prime is also negative. Does that ever happen? Well, let's go back to our interval. Here we're decreasing when we're less than when we're less than 0, when x is less than 0. However, we're concave up. Okay, you can see here we're concave up, so that's out. Here we're decreasing, and the question is there anywhere where we are concave down? Well, if you look right here on this interval from 0 to 2, we match. We are both decreasing and we are concave down. Okay. Now, we are decreasing from 2 to 3, but the problem is we're concave up, so that's out. And we are increasing from 3 to infinity, but we're concave up. So the answer to where are we decreasing concave down would be from 0 in interval notation, from 0 to 2, not inclusive, because at 0 there's an inflection point, and at 2 there's also an inflection point. All right, I hope that helps.